And I want to look at my next two counting techniques, which are combinations and permutations. The idea, I want k stages of a task, sampling without replacement, so once I move something, it does not go back in, from the same group of n units. So I have a group of n things, and I want to select k of them. And so the first thing we need to look at is it ordered or unordered? Does the order matter whenever I'm looking at this? Does the order that I select things in matter or not? If the order matters, then we use a permutation. And this is denoted as either p, k, n to let us know we're selecting k things out of a total of n, or NPK, we have the total number of things we have and the number of things we want. If order doesn't matter, then we use a combination. This is denoted by C. So CKN, where we put the number of things we want, total number of things we have. Or NCK, the number of things we have, the number of things we want. And it's also denoted by this NK stacked on top of each other in parentheses. So all three of these represent a combination. So let's take a closer look at each of these. Let's start with the idea of permutations. The permutation of k elements out of a total of n, so pk, n or npk, is given by n factorial over n minus k factorial. So let's talk about what this factorial is, this exclamation point. 3 factorial is 3 times 2 times 1. 4 factorial, 4 times 3 times 2 times 1. 5 factorial, 5 times 4 times 3 times 2 times 1. And so this is the idea. We're going to multiply a number by all of the whole numbers that are smaller than it. And it's also important to note that 0 factorial is actually equal to 1. And this will come in handy because occasionally if we want to consider NPN, then we would have n factorial over 0 factorial. So let's look at some examples of permutations. The lineup or batting order is a list of the 9 baseball players for a team in the order they will bat during the game. So how many lineups are possible? Well, we have a total of 9 players. Order is going to be very important, and we want to pick 9 of them. So our formula says 9 factorial over 9 minus 9 factorial, or 9 factorial over 0 factorial. As I stated previously, 0 factorial is just 1, so this is the same thing as 9 factorial. Next, the Department of Transportation plans to assign 6 civil engineers to oversee 6 interstate safety design projects. How many different assignments of civil engineers to projects are possible? Well, we have a total of 6 engineers and 6 projects. And the order is important because if I pick them in a different order, then they're assigned to different projects. So this is 6 factorial over 6 minus 6 factorial. The same thing as 6 factorial over 0 factorial, or just 6 factorial. Next, let's talk about combinations. So as a reminder, combinations means order does not matter. A combination of picking k elements out of a total of n objects is denoted by this parentheses with the nk. NCK, or ck, n. This is the permutation of k, n divided by the permutation of k, k. Or n factorial divided by k factorial n minus k factorial. So let's look at a couple of examples of combinations. 2 cards are going to be selected from a deck of 52 cards. How many outcomes are there if the first card is given to player 1 and the second card is given to player 2? In this case, this would be a permutation. Order does matter. If I switch the order of the 2 cards, that would be different since player 1 would then have a different card. We have a total of 52 cards and we want to select 2 of them. So this is 52 factorial over 52 minus 2 factorial, which is 52 factorial over 50 factorial. This gives us a total of 2,652 possible outcomes that could happen. Now let's change the problem slightly. We're still drawing 2 cards, but this time both cards are given to player 1. So in this case, the order that player 1 is given the cards doesn't matter, so it's a combination. 52 combination 2. So we would have 52 factorial over 2 factorial times 52 minus 2 factorial. So in this case, 52 factorial divided by 2 factorial, 50 factorial. Working this out, we get 1,326. There are less possible outcomes that could happen here. So let's do a few more examples of permutations and combinations. How many binary sequences, so sequences of zeros and ones, of length 10 with exactly 4 ones can be formed? So let's think through this problem. We have 10 spots and exactly 4 of them can be ones. So if I pick 4 places for my ones to go, it's guaranteed that the rest are going to be zeros. So really what I need to do is figure out where to place my 4 ones. So I have a total of 10 places, and I'm going to select 4 of them. The question is, does order matter? And in general, no. Because if I put this one here and this one here, or if I switched these 2 ones, they would still be the same number. So we get 10 factorial over 4 factorial times 10 minus 4 factorial. Or 10 factorial divided by 4 factorial, 6 factorial, which is 210. So there are 210 ways to do this. Now, if a binary sequence of length 10 is selected at random, what's the probability it has 4 ones? So I want to know the probability that there are actually 4 ones in a random string. Well, we just said there are 210 different strings that have 4 ones in them. And in a previous video, we showed that there's actually 2 to the 10 power number of possible sequences of length 10. So we have 210 divided by 2 to the 10th power. Let's do one more example. In the game of poker, each player receives 5 cards dealt from a deck of 52 cards. A full house refers to a 5-card hand that consists of 3 of a kind and 2 of a kind. So an example of a full house is a hand consisting of 3 10s and 2 5s. I want to find the probability that a randomly dealt 5-card hand is a full house. Let's start with the 3 of a kind. There are 13 different cards that we could have a 3 of a kind of: ace, 1, 2, 3, all the way up to 10, jack, queen, and king. So we need to pick which cards we are having 3 of a kind on. And this will be a combination since there's no real order here. There's no order to worry about since we're just picking one. After that, once we have that, there are 4 cards of that type, and we need 3 of them for 3 of a kind. So 4C3. But once again, C, since the order I'm dealt the cards in does not matter. We also need a 2 of a kind. Well, we've already got a 3 of a kind here, so there's actually now only 12 different types of cards that we could have a 2 of a kind of. And this time, out of those 4 cards, we only need 2. And I need both of these things to happen, so I need to multiply them. This is a probability, so we're going to divide by the total number of possible hands. There are 52 cards, and we're going to select 5 of them. And if we work this out, we get 0.00144. So this is the probability that a randomly dealt 5-card hand is a full house.